Hello, good evening. So today we have our tutorial session 8. So this session is based on the content of week 9 uh, and we will try to solve some sample numericals based on the content of week 9. So this will be helpful to uh, address some of the assignment questions. Will help you to solve those assignment questions which is due on coming Wednesday. So for today's session, let me just tell you uh, for this week 9 content, we have basically the octave simulation of perpendicular polarization, and the second major topic of discussion in this week 9 is the dielectric ideal conductor interface. Okay, so we already discussed in the last week about last week and last week we have discussed about plane waves at normal incidence and then plane waves at oblique incidence, where we discussed the perpendicular and parallel polarization as two cases. And this octave simulation, if you have gone through the video lectures, you would have understood how do we visualize the perpendicular polarization with the help of the octave uh, code. Okay, so then the major topic of discussion in this week 9 is dielectric ideal conductor interface. So far we have discussed a dielectric interface. So in this week the concept is slightly changed. We have a dielectric and a perfect conductor or an ideal conductor interface. Okay, so the very basic idea is at this interface there is total internal reflection. So if a wave is incident at some angle onto a perfect conductor, there is perfect reflection from that surface. Okay, and we know that this theta I is equal to theta r. Okay, so now let's go into the details of this dielectric ideal conductor interface, and we'll try to solve some sample questions based on that, which will help you because most of the assignment questions are based on this particular ideal dielectric and ideal conductor interface. So before moving to the sample problems, so let me just give a brief intro to this particular interface. Uh, so let's refresh the concepts of the idea of vectors, the direction vectors, and also the electric field and magnetic field vectors. Okay, so let's see. We have a let us draw a schematic first so that our concepts are clear. So we have x is z and y is normally outward, and you imagine that there is an incident wave coming in this direction. So this is my ki vector. Okay, ki vector is the incident wave vector or incident wave direction vector, and then there is a reflection because this at this interface on the other side of this is basically a ideal conductor whose sigma is infinity, and we know that there will be total internal reflection, and so this is our kr vector, that means the reflected wave vector. Okay, now let's have a look at the angles once. So this is theta I and this is theta r, where theta I and theta r are same. And now let's look at the electric field and magnetic field vectors. So if ei is normally outward. So that means the electric field is perpendicular to the plane of incidence. So here we have a perpendicular polarization, and then say if this is the magnetic field vector HI, incident magnetic field vector. So this HI can be resolved into two components. Say HI will have a positive Z component and a negative X component. Okay, so those can be determined with the help of this theta I. So that will be your magnetic field having two components, X and Z components. Okay, incident magnetic field. Now, so in this case of a dielectric ideal conductor, so this side is a dielectric and the other side is the ideal conductor. So that's an interface, and the wave is incident at an interface between these two. Now, the reflection coefficient and transmission coefficient, we have a clear idea. There is no transmission, so into the ideal conductor, so we say transmission coefficient is 0 and reflection coefficient is 1. That is, the wave is fully reflected back. That is a total internal reflection. Now, the other point to consider here is, let's have a look at the reflected field vectors. So when we say reflected field, so this is the direction of direction vector. Now the field can be written as, this is ER, this is HR. Okay, so I think we denoted everything, and now let us try to write EI, that is the incident field vector, that is EI naught, okay, that is the amplitude of the incident field vector, into e raised to minus j beta 1. So beta 1 is the phase constant of the first medium, that is the dielectric. Okay, e raised to minus j beta 1 into, now let's see this ki vector. So we are going to represent the ki vector. So ki vector can be resolved into two components, that is plus x and plus z component. So how do we write it? And let's see, this is, say if this is theta I, then this is also theta I. So cos theta I component is z. Okay, so sine theta I into x plus cos theta I into z. So that is your wave vector. Now incident field, incident electric field is in the y direction. So let me put the direction y cap. Okay, so that is your incident electric field. Now let's see what is incident magnetic field. So when we say incident magnetic field HI, so that is EI naught by eta 1. Okay, so EI naught by eta 1 into e raised to minus j beta 1 into, so incident wave vector is same, so we will repeat the same, sine theta I into x plus cos theta I into z. Now how about the direction of HI? So direction of HI, so HI has z and x components. So if this is theta I, we can say again this is theta I and this is also theta I. So this x component will have a cos theta component. Okay, so and that is in the negative direction. So minus cos theta I. So let me write it here, minus cos theta I into x cap, and the other is plus z. So plus sine theta I into z plus z cap. Okay, so that is the direction of the HI vector. So this is EI vector and this is HI vector. Okay, similarly we can write ER and HR. Okay, so to write ER and HR, what do we need to consider? We need to think about the reflected wave vector. Okay, so let me quickly write that. ER is ER naught e raised to minus j beta 1 into, now see, kr vector will be resolved into two components, plus x and minus z. Okay, so how do we write it? Minus z cos theta I plus x sine theta I. Okay. Similarly, the reflected magnetic field can be written as ER naught by eta 1 into e raised to minus j beta 1 into the wave vector remains same. So now we have missed out something. So the reflected electric field is again in the y direction. So y cap. So e raised to minus j beta 1 into minus z cos theta I plus x cosine theta I. So reflected wave vector is same. So we repeat the same. Now you see what is the direction of the magnetic field wave vector. So that is HR. HR can be resolved into two components. So that is plus x and plus z component. So cos theta I into x cap sine theta I into z cap. Okay. So these are the two components. So that's about the reflected electric field. So now let's see the let's see how to solve some of the sample questions based on this basics. Okay. So to discuss the very first question of today's session, a right circularly polarized plane wave in air is incident at the Brewster angle. Okay, so some plane wave is incident at a Brewster angle. Okay, so that is theta I is equal to theta b, and we also know that it is a right hand circularly polarized plane wave. Okay, it's incident on a semi-infinite slab of plexiglass. Okay, so we have a plexiglass which is a semi-infinite slab. So whose epsilon r is 3.45. So plane wave, RHCP plane wave is incident at theta I is equal to theta b. Determine the fraction of incident power that is reflected and transmitted at the interface. So we have an interface here. So what is our interface here? Air, and this is what? Dielectric. So we have an air dielectric interface. The question is on how much power is reflected, how much power is transmitted at the interface. So this is not a dielectric ideal conductor interface, but let's try to solve this to refresh our concepts on air dielectric interface. So to start with, what is Brewster's angle? Okay, so we have if you have gone through the video lectures, you have come across this equation of Brewster's angle, that is tan inverse of root of epsilon r. Okay, if the first medium is air and the second medium is having a dielectric of epsilon r equal to 3.45, you can write down tan inverse of root 3.45. This gives us an angle of 61.7 degree. So this is the Brewster angle or the angle of incidence. Okay. Now when a plane wave is incident at the Brewster angle, the gamma parallel, that means the reflection coefficient for parallel polarized component becomes 0. Okay, that's the idea of Brewster's angle which we discussed in the last week. So now let us write the Snell's law at this in air dielectric interface. N1 is in air, N1 sine theta I is equal to theta B. So let's write theta B is equal to N2, which is the dielectric, into sine theta T. So that is the angle of transmission. So this is angle of incidence and this is angle of transmission. Now can we calculate the angle of transmission here? Okay. So how do we calculate that? Theta T is equal to sine inverse of N1 is 1, so sine theta B. Theta B is sine 61.7 divided by what is N2? Root of epsilon r, root of 3.45. So if you take this, if you do this calculation, you will get theta t, that is the angle of transmission, as 28.3 degree. Okay. Now, now what is the reflection? So the question is on how much power is reflected back. We already know that if the angle of incidence is equal to theta b or Brewster's angle, the polarized reflection coefficient, component, parallel polarized reflection coefficient is 0. So now, so therefore, look at the perpendicular component of reflection coefficient. Let me write down the equation for you. Eta 2 cos theta I minus eta 1 cos theta t divided by eta 2 cos theta I plus eta 1 cos theta t. Okay. Now let's try to substitute. Eta 2 is the dielectric. So let me write it as eta naught by root epsilon r into cos 61.7 minus eta naught. Eta 1 is the AL. So eta naught cos theta t is 28.3 whole divided by eta naught by root epsilon r cos 61.7 plus eta naught cos 28.3. So if you simplify this, you will get the reflection coefficient as minus 0.55. Okay, so that is your reflection coefficient. Now what is power? So power is square of reflection coefficient. So gamma square, if you take, you will get it as 0.303, or I can say 30.3%. Okay, 30.3% is getting reflected back. So now let us see, is it all 30%? Now see, a wave, a plane wave, RHCP plane wave is incident. So this has a perpendicular component and this also has a parallel component. In this, so the incident power, half of the incident power is in the perpendicular component and the other half of incident power is in the parallel component. Now, when we say reflected power, so this 30.3% is including both. Okay, so so that when we say in reflected power, so in case of perpendicular component, we have only 30.3 by 2, that is 15.2% getting reflected, because only this half of the incident power was in this perpendicular component. Parallel component, because it was incident, so parallel component had the half of incident power. Because it was incident at theta b, the Brewster's angle, there is no reflection. Okay, so reflection is basically in the perpendicular component. So take the half of them. So this 15.2% is reflected back. Okay, out of the total incident power. Okay, so 15.2% is reflected back. Now how much is the transmission then? PT is equal to 100 minus 15.2, which is nothing but 84.8%. Okay, so that is your fraction of, out of the fraction of incident power, how much is reflected and how much is transmitted at the interface. Okay. So coming to the next question. So electric field associated with a plane wave propagating in air with an arbitrary direction is given by. So electric field is given. Electric field is given. Okay. So it is mentioned that this field is associated with a plane wave propagating in air in a particular arbitrary direction. You see the direction is having x component, y component and z component. So it is very clear that it's having an arbitrary direction. And you see the wave vector has x and z components. So it is clear that the plane of incidence, okay, the plane of incidence is xz plane. Okay, if this plane wave is incident on a perfectly conducting plane. So here now we have an air perfectly conducting conductor interface. Okay, so one side is air and the plane wave is propagating in air, and it is now incident on a perfect conductor. Okay, and uh, so this perfectly conducting plane whose normal is oriented along z-axis, sketch the figure and find the following. So now let's start with sketching the figure so that this concept becomes easy to grasp. Let's start with the sketch. You have xz plane as the plane of incidence, xz plane, and it has been mentioned that so there is a perfect electric conductor whose normal is oriented along the z-axis. Okay, so this normal to this PEC is along the z-axis. So this is y, which is normally outward. Then now the wave is incident. So wave was propagating in air and it is incident on the interface. So wave, let us assume that the wave is coming in this direction with the vector ki vector. Okay, and because at this interface it will have a reflection, so this is your kr vector. Okay, now so what is our understanding from this electric field equation? So electric field equation, always remember, so this is our incident electric field, what is given in the question. This is our incident electric field. See, that incident electric field will have basically a parallel component and a perpendicular component. Okay, so we see that it has x component, y component and z component. So which is the parallel component and which is the perpendicular component? So we have our plane of incidence as xz plane. So y component is our perpendicular component. Okay, so this perpendicular component is nothing but 4y cap, and the parallel component, okay, which is parallel to the plane of incidence, that is your 7.83 x cap plus, oh sorry, not plus, minus 4.5 z cap. Okay, this is your parallel component, the other is your perpendicular component. Okay, Now, if this is incident on, okay, now let's move on to the wave vector part. So looking at the wave vector, what is our understanding about wave vector? You see e raised to minus j 7, so this is beta into 0.5 x cap plus 0.87 z cap. Okay, so if this is the wave vector associated with the incident field, so what is Ki? Ki has what component? If you try to resolve Ki, say Ki is in this direction. If you try to resolve Ki, Ki will have a plus Z component and plus X component. Okay. Now let's draw the angle also. So this is theta I. This is theta R. If this is theta I, then this is also theta I. So z component is the cos theta component. Okay. So cos theta I is equal to 0.87. Sin theta I is equal to 0.5. Okay. Solve any of this. You will get what? Theta I. Okay. Theta I. Sin 30 is 0.5. It's very clear. So theta I is 30 degree. Okay, that's how we get the angle of incidence. Okay, now moving on. So at the interface, so because we have a perfect conductor on the other side whose sigma is infinity, for which the eta 2, that is the impedance of the second medium, is 0. Okay, now what will happen? Gamma parallel, that is the parallel polarization reflection coefficient, is 1, and gamma perpendicular is also 1. Okay, gamma perpendicular is also 1. So therefore ER parallel, if you take the magnitude of ER parallel, which is equal to ER EI parallel. Okay, ER parallel magnitude is equal to EI parallel. Similarly, ER perpendicular magnitude is equal to minus EI perpendicular magnitude. Okay. So this is this one. Okay. Now let's start with writing the expression. So what is given to us is the incident field, electric field. So what the first question is parallel component of the reflected electric field. So let us first find out the reflected electric field parallel component. So that is ER parallel. Okay. So ER parallel, to write ER parallel, what do we need? We already know what is EI parallel. Okay. I told you EI parallel is this component. So 7.83 x cap plus 4.5 z cap e raised to minus j7 into, you see the kr vector is in this direction. If you resolve, you will have two components, x and minus z component. So e raised to minus j7 into 0.5x minus 0.87 z. Okay, so that is your ER parallel. Now let's see what is ER perpendicular. ER perpendicular. So what is EI perpendicular? That is 4y. So minus 4y cap, okay, multiplied by e raised to minus j7 into, so the wave vector remains same. So 0.5x minus 0.87 is z. Okay. Now you see the parallel component of reflected electric field has x and z component. Perpendicular component of reflected electric field will have y component. Okay. Now moving on to total electric field. So which is your third part. So second part is perpendicular component. So that also we have found. Total electric field in the region z less than 0. So this is basically in ER parallel plus ER perpendicular is the total reflected electric field. So if you add it with EI, then it becomes the total electric field in the region 1, that is Z less than 0, or I can say in the air. So ER parallel plus ER perpendicular will give us the total ER total. Now E total in medium 1, that is in air, we can say EI plus ER. Okay, so add these two components and then add it with the initial EI component, you will get the total electric field, which is the C part of this question, answer to the C part. Now coming to the D part, how do we find the D part? Parallel component of the reflected magnetic field. Okay, then E part is perpendicular component of the reflected magnetic field. So to get both of them, first of all we should have parallel component of the magnetic field. Okay, incident magnetic field. So if you know what is incident electric field, we can find out incident magnetic field. From the incident magnetic field, which is having a parallel component and perpendicular component, we can come to parallel and perpendicular components of the reflected magnetic fields. Okay, so that's the crux of this, that's how we solve this question. So let's move to the D part. So to take the D part, how do we do the D part of this? So let us start. So what is given in our question is EI. Okay, EI is having EI parallel and EI perpendicular. Okay, from this EI parallel, we'll be able to calculate what? HI parallel. How do we calculate that? EI parallel magnitude divided by eta, that is eta naught, because it's in air. Then e raised to minus j7 into, again, incident wave vector. Remember, it's an incident wave vector. 0.5x plus 0.87 z. Okay. Then so EI parallel. So let's see what is EI parallel here. So your incident field vector EI parallel is 7.83 and 4.5. Two components are there. So take the magnitude, square root of 7.83 square plus 4.5 square. We'll get it as 9. So 9 by eta naught e raised to minus j7 into 0.5x plus 0.87 Z. Okay, that is your HI parallel. Now let's come to EI perpendicular. So from EI perpendicular, let's calculate what? HI perpendicular. How do we do that? EI perpendicular by eta naught into so and so. I mean the incident field vector we have to write. So when we say EI perpendicular, magnitude of EI perpendicular by eta naught e raised to minus j7 into 0.5x plus 0.87 is Z. Okay. So what is EI perpendicular magnitude? 4. So we can write it as 4 by eta naught e raised to minus j7 into 0.5x plus 0.87 is Z. Okay. Now let us look at the reflected fields. HR parallel. Okay. HR parallel and HR perpendicular. Okay. So how do we get that? ER parallel by eta naught and this from HR ER perpendicular by eta naught. Okay. So the similar way, see that the reflected wave vector kr is used in the e raised to minus j power term, and see, look at the field vectors of the incident field and reflected field, electric field, and reflected magnetic field. Okay, that's how we go on and solve this question. So total magnetic field, last part of this question, you see total magnetic field in the region 1, that is Z less than 0 in air. What is the total magnetic field? So H is equal to HI, that is incident field plus reflected field. So this HI will have HI parallel and HI perpendicular, and HR will also have HR parallel and HR perpendicular, 2 components each. So that is how we solve this kind of a question. So now let's move on to another question. So the question, let me read it. The effect of total internal reflection is observed by shining the green laser pointed under 45-degree internal angle onto the base of the prism. So see, in this figure we have a prism right here, and this prism, there is a green light which is being shined in this particular direction onto the base of the prism. So this is the base of the prism. Okay. So green light is shined on to the base of the prism. So this is the green laser, okay, which is having a wavelength of 532 nanometers, and inside this prism, I mean it's a glass, basically it's a glass having a refractive index of 1.5, which is also clear that it is square root of epsilon r. So square root of 2.25 is 1.5. Okay. So, and this is being incident at an angle of 45 degree onto the base of the prism. Okay. So this angle of incidence, this angle is 45 degree. Now the question is, so we all know that in the prism what happens, we all know that there is a total internal reflection which is happening here, and uh, the question is not about that. Question is about at what distance from the surface at which the total internal reflection takes place. So this is the surface at which the total internal reflection takes place. At what distance from the surface in the air is amplitude of the evanescent wave 1 by E of its value at the surface. Okay. So at the surface, evanescent field has some amplitude. When will that reduce to 1 by E of that value? At what distance it reduces to 1 by E of the original value at the surface. So to solve that question, we should know the expression for an exponentially decaying evanescent wave, which is discussed in the video lectures. E raised to minus Ez 2 pi by lambda into square root of n1 square sine square theta I minus n2 square is equal to, so this is the expression of the exponentially decaying uh, evanescent field vector, evanescent field. Okay, so if you see, this is Z, that is the distance, 2 pi by lambda, lambda is the wavelength, n1, here you remember n1 is the glass and n2 is air. Okay, so green light is being shined onto the prism, total internal reflection takes place, and in air, at what distance evanescent field will have an amplitude 1 by E. Okay, or I can write it as E raised to minus 1. Okay, so equating either sides, we can easily write it as Z 2 pi by lambda root of n1 square sine square theta I minus n2 square is equal to 1. Now Z is equal to lambda by 2 pi. So this is square root. So let me write it as n1 square sine square theta I minus n2 square, the whole raised to minus half. Okay. What is lambda here? 532 nanometers by 2 pi into N1. N1 is the prism. N2 is the air medium. Okay. Light is shined onto the prism. So N1 is 1.5 square sine square theta I. Theta I we all know, it's given in the question, 45-degree internal angle to the base of the prism. So sine square 45 minus N2 square is 1 square because second is air, ray whole raised to minus half. So if you solve this, you will get the answer as 239 nanometers. Okay. So at this particular distance, the evanescent field's amplitude or the magnitude becomes 1 by E of the original value. So that is how we look at this question. So let's move on to a question, another question, which is to pick the true statements among the following. So this is regarding, so all these statements are regarding Brewster's angle at a pure dielectric interface. You can select one or more. Okay, so let us read through all of these statements and see whether it is a true or a false statement. Okay, so uh, regarding Brewster's angle. Okay, so it is when we say it is the Brewster, it is about the Brewster's angle. So Brewster's angle is well defined for propagation from both rarer to denser and denser to rarer medium, or it is defined only for propagation from rarer to denser medium, or it is or defined only for denser to rarer medium. So we know that it is A. So Brewster's angle is well defined for a propagation if it is whether it is from rarer to denser or denser to rarer. Both cases Brewster's angle is well defined. Okay, so B and C are wrong statements and A is a true statement. Now next statement, you see, it exists only for perpendicular polarization. Another option is it exists only for parallel polarization. So when if you have gone through the video lectures, we have got professor has gone through the derivation of Brewster's angle, wherein you see that Brewster's angle exists only in case of a parallel polarization, not in case of a perpendicular polarization. Now, another statement is it is the main concept used to guide light in an optical fiber. Is it? No, it is not the main concept used to guide light in an optical fiber. We all of us know in an optical fiber we have core and clad. Both are glass with the refractive index of N1 and N2, where N1 is slightly greater than N2, and in which there is a total internal reflection due to which light is being guided in the optical fiber. So Brewster's angle, not a true statement regarding the Brewster angle. Now coming to the last question, it exists for last statement, it exists for the both parallel and perpendicular polarization. That's not true because we already said it exists only for parallel polarization. So next question. So to discuss the next question, uh, read through the statement to understand what is the scenario here. A fish is swimming underwater and looking upwards. Okay, so we have water here, and say if you have a fish out here, it's looking up. Okay, so here you or everywhere you have water, and the fish is looking up, and pick the true statements from below regarding the range of vision of the fish. Okay, so if the question is or the statement is about the range of vision of fish which is underwater who is looking upward, okay, and assume refractive index of water n is 1.33 and the water is clear, so that means it's not muddy, so it's a very clear water. Okay, so now select one or more. The fish has a full range of vision of the world above the water line. So this is our water line, maybe the surface, we can call it the surface. So whether the fish has the full range of vision of the world above the water line. That is one thing. Second statement, due to total internal reflection, fish can't see anything above the surface of water. Okay. Then the third statement, fish can see the world above the water line only within a cone of half angle of 24.4 degree. Okay. So fish can see only a half angle of some particular angle. There is a critical depth below which total internal reflection prevents any view of the world above the surface of the water. So is there a critical depth uh, below which there is total internal reflection total internal reflection, that means say the ray is traveling back and there is no view of the world above the surface of the water. Okay, and the last statement is fish can see the world above the water line only within a cone of half angle of 48.8. Again, it's some particular half angle only the fish can see, that is some 48 degree. So which of these statement is true? That is the question. To answer this question, see the total internal reflection. So when we say total internal reflection, uh, so if you look at this figure over here, this arrow shows, so the black arrow and the red arrow. So the red arrow is showing the transmitted wave. Okay, and see this. So this is in this angle. So this red arrow is just at the surface of the water line. Okay, so this denote that the entire world above the surface is seen by the fish. So this total internal reflection is not going to affect the range of vision in the rarer medium. Rarer medium is the surface above the water line. Okay, so this first statement, that is the fish is having a full range of vision of the world above the water line. It does not have any uh, restriction to the view or the range of vision. Okay. So if you look at this more clearly, so if both the ways, so this is one way and this is this way. Okay, so if you reverse this path, okay, reverse this path and imagine like this. So this is the view of the fish. Okay, light rays are coming like this. So coming to the next question, pick the true statements about reflection of a wave incident from air onto a perfect conductor. So we have air and perfect electric conductor, and you see the wave is getting reflected. So this is incident and this is reflected. So say for this we can say the incident field, it is the incident electric field which is associated with the incident wave in this direction. So if that incident wave has some polarization, what happens to the polarization of that reflected field, or what happens to the reflected electric field? So in terms of polarization, let us discuss that. So to start with that, let's have a background of this. Assume that your electric field, okay, it's in an arbitrary direction. So it is an electric field associated with the incident wave in a particular direction. It's having an arbitrary direction, means it can have any x, y, z component. So I can say that, or I can divide it into two. One is the EI parallel and the other is EI perpendicular. That means one component is parallel component, which is basically parallel to the plane of incidence, and the other component is perpendicular to the plane of incidence. Okay, so this electric field, incident electric field, can be uh, expressed as, okay, can be expressed as uh, the combination of two, that is EI parallel plus EI perpendicular into say e raised to j phi. So this is an arbitrary angle phi, which is the angle between the parallel component and the perpendicular component. So let's say assume, so these are the two components. Let's say assume that angle between those two components is 0. Okay. So if angle between the parallel and perpendicular component is 0, then we say that the incident field is linearly polarized. Okay. Now, what will happen in this particular case of linear polarization, or that is, so this say, let me say that this is case 1. In this particular case of case 1, that is when phi equal to 0, that is when the electric incident field is linearly polarized, what happens to ER? Okay, let me write ER as ER parallel and ER perpendicular. So ER parallel is gamma parallel into EI parallel, then ER perpendicular is gamma perpendicular into EI perpendicular. Okay, so this is your reflected electric field, that is parallel component and perpendicular component. Now adding these two, okay, ER parallel plus ER perpendicular, you will get the net reflected electric field. Net reflected electric field. So here the question is gamma parallel and gamma perpendicular. Is it same? No. Gamma parallel is not equal to gamma perpendicular. Therefore, ER parallel will never be equal to ER perpendicular. So, if EI is linearly polarized, then ER will also remain linearly polarized. Okay, the linearly polarized wave remains linearly polarized after reflection. So, the first statement regarding the reflection of a wave is correct. That is a linearly polarized wave. So incident wave is linearly polarized. The reflected wave is also linearly polarized. Only thing is the magnitudes are not same. ER parallel is not equal to ER perpendicular, but it is linearly polarized. Now let us move to another case 2 to discuss. Assume that this particular phi is 90 degree plus or minus pi by 2. Okay. So if it is plus or minus pi by 2 and also EI parallel is equal. So magnitude of EI parallel is equal to magnitude of EI perpendicular. Then we say EI is circularly polarized. So if it is an incident, that means the incident field is circularly polarized. Then how about the reflected field? So let's have a look at what happens to the reflected field. Now here again gamma parallel is not equal to gamma perpendicular. Therefore ER parallel magnitude is not equal to ER perpendicular's magnitude. Okay. Now what will happen? The magnitude of the reflected fields are not equal. So the circularly polarized incident wave will definitely become what? An elliptically polarized electric field. So circular polarization cannot be maintained after reflection. So let's look at the statement E here. A circularly polarized wave cannot remain circularly polarized after reflection. Okay, so these are the two correct statements. So in case of circularly polarized incident wave, because gamma parallel is not equal to gamma perpendicular, parallel is not equal to ER perpendicular. There itself the magnitude condition is being violated. So circular polarization cannot be maintained. So it becomes a elliptical polarization. Okay. There is one more correct statement among this, that is all power is reflected back by the conductor. That is very true because there is no field going inside the conductor, a perfect conductor. All the power is being reflected back. Okay. Now how about the statement B? A circularly polarized wave remains circularly polarized. No, that's not true. Coming to the statement C, a strictly elliptically polarized wave can get converted to circularly polarized wave after reflection. Is there a chance? So imagine that chance. EI parallel is not equal to EI perpendicular. Okay. So incident is elliptically polarized. Now in that case, multiplying that by gamma, the reflected electric field, is there a chance that that can be equal? So that is not possible. That is not true. Coming to the statement F, linearly polarized wave cannot remain linearly polarized. That's not true. We have seen the case 1. Linearly polarized wave can definitely remain linearly polarized because there is no phase difference again there. Only difference is in the magnitudes. So because gamma parallel is not equal to gamma perpendicular, ER parallel magnitude is not equal to ER perpendicular magnitude. Even if the magnitudes are not same, it will remain linearly polarized. Okay, because the phase, there is no change in phase, it's always 0. Coming to the statement G here, what is that? Some fraction of the incident power is lost into the conductor. There is no way that it can happen. There is no transmission into the conductor and therefore there is no power lost into the conductor. Okay. So the if you see the power, all the power is being reflected back by the conductor and even if the evanescent fields exist, that happens in the surface of this interface. So to give an idea of the questions for the assignment 9, so if you see, the questions are mainly on the dielectric ideal conductor interface. Say the first question you see, the electromagnetic wave polarized along y-axis incident on dielectric ideal conductor, and which of the components will be non-zero at z equal to 0. So we can imagine at the interface what are the boundary conditions. If you know those boundary conditions at the right way, you can answer this question. Now coming to a few more questions. Again, it's at the interface, what is the sum of incident and reflected field, and when that is zero. Okay, so the sum of incident and reflected field is zero for what condition? Is it for perpendicular polarization? Is it for parallel polarization and all that? Coming to this, so what does the reflection coefficient depend on? Okay, so we have looked at the equations. So reflection coefficient at the dielectric ideal conductor, uh, what it is dependent on? What is the reflection coefficient dependent on? Is it dependent on the angle of incidence? Is it dependent upon the polarization of the EM wave? Is it dependent upon the characteristic impedance of the dielectric medium? Or is it about the phase of the wave at that particular interface? Okay. Coming to a fourth question. What is the fourth question? Again, for a normally incident EM wave on a dielectric ideal conductor interface, what is reflection coefficient? Okay, very easy question. So just look at what is being asked. There is a normal incidence and it is a dielectric ideal conductor interface. Now coming to this 5th to 10th question, they are connected question. If you look at this, for a perpendicularly polarized EM wave in a non-magnetic dielectric medium incident on the dielectric ideal conductor interface, total electric field in the dielectric medium is given as. So here the question is, on a dielectric medium there is a perpendicularly polarized EM wave. Okay, so that is having a y component. You see there is a component. So that is your perpendicularly polarized electromagnetic wave. Okay, and it is incident on a perfect conductor. So the question, so this what is given is the incident field. Okay, so if you know the incident field, electric field amplitude of the incident EM wave, very easy question. So what is the amplitude of this incident EM wave? Then what is the angle of incidence? So if you look at this particular expression, you will know what to write. Okay, so what is the amplitude of the EM wave and what is the angle of incidence? So angle of incidence is always given by the vector, wave vector. So from that we can write what is the angle of incidence. Then what is the refractive index of the dielectric? So refractive index of the dielectric can be found. Then question is on the eighth question is on the wavelength of the EM wave. So that is evident from the e raised to j omega t term in this equation. You can come to, or e raised to j beta term, you can come to the wavelength. And coming to this characteristic impedance of the dielectric, again that depends upon the that is evident from the, again from this we can solve this out for the characteristic impedance. What is eta? Given that the surface current density of the conductor is equal to the tangential magnetic field. Okay, so surface current density is Js. So Js is equal to tangential magnetic field. Then you need to calculate the amplitude of the surface current density. So this is about the vectors are getting equated. So if the vectors are equal, that means the surface density current density vector is equal to tangential magnetic field. So take out the tangential magnetic field, equate it to current density, and find out the amplitude. So find out the amplitude of that vector. Okay. So finding the magnitude of the tangential magnetic field will give us the magnitude of the surface current density. So these are some of the hints to solve these assignment questions.